propellant considerations for launch vehicles. We'll discuss what propellants are available, what their traits, values, pros, and cons are. We'll look at feasible regions for single-stage to orbit launch vehicles, data on first stages, numerical results for two-stage to orbit launch vehicles as well. So let me give an historical note. The Saturn V, which was the giant rocket that took men to the moon, used liquid hydrogen and liquid oxygen, which give very high ISP, for the second and third stages. But it used kerosene and liquid oxygen, which provides a lower ISP for the first stage. And the question is, why do they pick a lower specific impulse for the first stage? According to the Space Propulsion Analysis and Design book by Humble, Henry, and Larson, in the first stage, if we had used the more efficient liquid hydrogen, liquid oxygen propellants, it would have been too big to transport to the launch site. And so you have to wonder, why is that? What makes the rocket bigger? And I've done a rough calculation to say how big it might be. Here's a picture from Baker's book, The History of Manned Spaceflight, of the vertical assembly building, which is a cube, 500-foot cube. So in other words, it's 500 feet by 500 feet by 500 feet. And when it was first made, was the largest building by volume in the world, and it's still one of the largest buildings by volume. Here you see the Saturn V loaded up and on its way out to the launch pad. It's just coming out of the giant doors of the vehicle assembly building. And that rocket was about 363 feet tall. So you see that it is neatly fits into the vehicle assembly building. But if you replaced the first stage with hydrogen LOX, because its density is so much lower than that of kerosene LOX, the first stage would become much bigger, and for the moment I'll just assume we increase the length, and it could get as high as 540 feet, which certainly pokes you through the the roof of the vehicle assembly building, and even if you made it shorter and squatter, it would still be very near the ceiling, making it difficult to use cranes and so on to assemble the vehicle. You know, that extra distance over the 363 feet here was needed in the vehicle assembly building to put the rocket together. So if we look at the maximum density ratio that you can have between kerosene and liquid oxygen versus liquid hydrogen and liquid oxygen, it's about 1,000 kilograms per cubic meter divided by 200 kilograms per cubic meter. So it's can be as high as a ratio of 5 to 1. Now, the hydrogen LOX is more efficient, and so you would only need about half as much propellant by mass in order to achieve the same delta V the first stage achieves. But if we use about half the mass, you see that you'll still be about 2.5 times the volume. So if you make the first stage 2.5 times bigger by volume, then you have this sizing difficulty. And so, as they say in the SPAD book, choice of propellant depends in part on density of the propellant. If we use denser, lower ISP propellant for the lower stages, we can keep the size low. And then we can use less dense, higher ISP for the upper stages. So this has become kind of a rule of thumb for very large, heavy lift launch vehicles. It's not an absolute, but it is one. It's a principle that's been accepted for many years as a guiding rule on very large launch vehicles. Now let's consider what propellants are available, and I just want to talk about for launch vehicles. Because the question of propellants in general is a vast one. It's a very big subject. And even if we strict the question to launch vehicles, there are lots of choices to think about. So here's, again, a table from SPAD. And we see the various technologies here. And let's look at, first of all, cold gas technologies. And we see that we have the disadvantage of low specific impulse. We have 60 for nitrogen and 250 for hydrogen. And so because of this low specific impulse, we're going to cross this off as not particularly good for launch vehicles. If we then go, let's skip down here to the nuclear. What we see are very high ISP values, up to 1100 seconds. Thrust as high as 12 million newtons possible. So we have this very high specific impulse, but we have the problem of unproven and politically unattractive. And these two reasons make it difficult to employ nuclear rockets for launch vehicles. In fact, Robert Zubrin, in his book The Case for Mars, specifically decided not to use NTRs, nuclear thermal rockets, because of the political issues far more than because of any engineering questions. So we're going to cross this one off too. Now what about electric? Well, look at these ISPs. 1,000, 7,000, 10,000 seconds. Huge. But what's the problem with it? Low thrust levels. Here are the values that you get. Up to 20 newtons. And that's for a very, very large vehicle. A vehicle that would be, say, of the order of 20,000 kilograms to provide, or more, to provide only 20 newtons. So this can only be used in space. We can't use that for a launch vehicle. However, in space, using basically electric propulsion engines is a viable option. But right now, we're concentrating on launch vehicles. And so let's see what it says here. Now, with the monopropellant, we see fairly small values in the liquid case, so probably that's not going to be real attractive. But for bipropellant, and there are many, many varieties, ISPs of 320 to 460 look very good. Solids also can get up to as high as 300. And hybrids, which is sort of an emerging technology, may ultimately become important. And so we have moderate performance, in other words, good performance, and some safety concerns, but we have high thrust, and heritage means we have a lot of experience with these kinds of rockets. And therefore, we're going to look at bipropellant, liquid and solid rockets in the analysis today, these two in particular. But as you can see, there are many, many choices to explore.